Hello, everyone. Can you guys hear me well?
Hello, yes, we can hear you.
Nice, very nice. Good morning. I hope you had enough sleep. So let's get straight to the previous lecture. This week we will not have, or at least this lecture, we will not have a quiz. So we will go through the previous lecture quickly, and then we finish the final part, and we go straight to the new lecture. Of course, next Monday, we're going to have a quiz again. So last time we spoke a little bit about what segmentation is. Then we spoke about thresholding as a method for segmentation. And then we spoke about edge detection. We stopped, I think, in calculations of image gradients. And after that, we will speak about erosion and dilation, which are very basic mathematical morphology computations. Yep. So as we said, image binarization is a very simple technique that's relied on global thresholding. Basically, we set a value, and for that value, if the content of the pixel is smaller than the threshold, we set it to 0. Otherwise, we set it to 1. So you can think of it as a very extreme form of contrast enhancement. So there are several segmentation methods. We have described bimodal histograms and Otsu's method and adaptive thresholding, but there are others that you can use. Yep, let's go directly, I think, to, yes. So as we said, there's usually inside an image two main parts that interest us. So there is the foreground or the background, which is this. And of course, there is the foreground, which is the objects you are interested in. If you lay down the values of these pixels in a histogram, so for example, a pixel with intensity 50, this is how many pixels we have. We get usually two big peaks in our histogram. So this is why it was called a bimodal histogram. So it's kind of similar to the bimodal distribution. So for example, in this situation, we also had the same thing with two main peaks. In general, one of these two peaks would be our background, and the other is the foreground, depending on whether it's a white object on a black background or a black object on a white background. And then we said that there are a lot of difficulties faced when you want to basically split this bimodal histogram. Mainly, we don't really know when you can't really make an algorithm that kind of looks at the histogram and decides these are the two peaks. And this is why we introduced Otsu's method, which is a very simple method. Basically, we're gonna parcour all of these thresholds and see which one gives us the best criteria. So the criteria we're working with is a smaller within class variance and a large between class variance. So in this case, let's take a small example just to understand what this means or refresh what that means. So if you take your threshold in this place, again, the variance in the right side is going to be small, but the variance of the left side is going to be huge, right? So this is a bad threshold. But if we take something around here, all of these points are kind of like they don't have any, all of these pixels don't have any representation in our image. So all of our pixels are close together here and they're clustered here too, meaning both of their variances is very small. And this is the criteria that Otsu's method is trying to achieve. Of course, the large between class variance is calculated based on having as far of what is it called? As far of this as possible, as far of means as possible. So trying to push them away from each other, right? We have done some calculations. I've seen the how to calculate the within class, how to calculate the between class variance, and seen when is this term at its highest and when it's this term at its lowest. Yeah, we've seen an example of how Otsu's method works. So Otsu's method, again, the goal of it is to give you the optimal threshold, right? So this is the goal of Otsu's method. After that, we spoke a little bit about band thresholding as a technique that exists. We didn't give any technique on our algorithm how to do it, but basically it tries to split it into two parts, or from two parts into three parts, like this. So background, background, foreground. Might work or might be useful in some pixels or in some types of images, but it's mostly done in order to get these contours, right? So it's good for edge detection. This band thresholding. It's kind of similar to segmentation, but only for thresholding, right? Or for contouring. Now, semi-thresholding, again, is another technique that we didn't give like an algorithm for because it's pretty simple. And what it says is instead of putting a 1 when you are above the threshold, basically you keep the original value of the pixel, right? So here we have, this is the original image. Now we are like combining both the mask with the original image, and you get the objects of interest in their original pixels, right? We've seen that this method works well, but there is one small constraint, which is, okay, sorry. There was one small problem, is that you really cannot always find this global optimal threshold, right? So if you have a picture this big, and you set up the threshold to be 150, even though that this is like the best threshold you managed to calculate, it is still not a good threshold. You see? So that's because sometimes there is no global threshold that works very well. So in this case, they decided to make another technique called adaptive thresholding, where we don't calculate this global threshold, but instead we work on smaller parts of the image. Basically, we will be working on local thresholds instead of global thresholds. Again, how can we calculate the thresholds in all of these different parts? Well, you can use Otsu's method. You could use adaptive mean thresholding, meaning we take the mean of the pixels in every place, or you can take the adaptive Gaussian thresholding, which is very similar to the mean, but instead of having the same weights, for example, here 1, 1, 1, 1, 1, 1, 1, we would have something like 5, and here we have 2, and we have 1, 1, 2, 2, 2, 2, 2, 2, 2, 1, 1, 1, 1, 1. So basically a filter that kind of looks like a Gaussian distribution. And all of them can calculate for you the optimal threshold, or the threshold that kind of works with. Nice. So adaptive thresholding, again, makes a very small assumption, which is that smaller regions have more uniform illuminations and tend to have better, like we can get better calculations of the threshold for them. So for example, just so you can see the differences. So this is the original image. You can see that the lighting in this place is not the same as the lighting in this place. So the global thresholding that we have studied before does not work very well, whereas adaptive mean thresholding gives even better results, but as you can see, it's more noisy. But so if we apply this adaptive Gaussian thresholding, we usually tend to get more clearer thresholding. Nice. So in practice, or about the neighbor side, in practice, it's much easier to find this optimal neighborhood size, or the size of this rectangle that we use to calculate the local threshold. It's much easier to find that one than it is to find or to fine-tune the global, what is it called, threshold, right? So usually there is a very broad range of these neighborhood sizes. Now, again, we spoke a little bit about what edges are. So we said that an edge is basically a sudden change. Are we recording? Sorry, one second, just to confirm. Yes, we're recording.
Yes, you're recording.
Nice. So basically, we said that an edge is a sudden change in the pixel intensity. So here we went from something that is a bit dark into something that is a bit lighter. So this is what an edge represents. Now, if we're looking in a 1D scenario, right? So let's imagine that the values were like very small here, and then suddenly they jumped or peaked and became very big. One very good way of detecting such changes would be gradients. So in here, usually if you're working with like, let's, for example, draw the gradients, right? So let's say this is the gradient. Here, this is like the gradient. This is the gradient. There is some change, but there's not like a big change in the values of the gradients, right? But here we are like sudden change in values of the gradients, right? Because usually the gradient is like, what is it called? So it's like this, right? I don't know how to say this in English. Yeah, so this, yeah, perpendicular or something like that. So you guys understood, you know gradients, I hope. So this is how we can use basically gradients in order to detect where these points are, but in 1D, right? So we haven't spoken about it in 2D yet. So for example, here we have this sudden change from white to black to white again. But now we're working only in this red line. Huh? We're not working on the whole image, right? We're still working in the 1D situation. So you can see the pixel intensities went from very white. They went down to something that is very black, and then we went back up to something that is very white. Now, how can you like parkour all of these values, or not parkour, like go through all of these values and detect the sudden changes? Well, simply you could say something like this, right? So probably like value in here minus the value in here. And if the change is too sudden or too big, then we make it like, you know, bigger than a threshold. We call this as an edge, right? You can do that. An easier way would be to use these derivatives, as we said. So it tends to give you very small values in here for something that is the same object or like the same environment, and then sudden change, and it goes back to being the same again. Sudden change, and it goes back to being the same again. Now, again, you would kind of like, this is in a perfect scenario where you have like 0 and then some value, 0 and then some value, right? This is the perfect scenario. But in most cases, you're going to have something like this and then a big value, and then something like this and then a big value, or like something like that, right? So this, again, like forces you to introduce the concept of what is a big enough change, right? So is this big enough or is this big enough? So they decided to use like the second derivative, which is an even easier calculation. So for the second derivative, things kind of get a bit simpler, right? So for example, the area of our interest no longer requires like some, as we said, local maximum or local minimum calculations, but only noticing when does the function go from a positive value to a negative, right? When we cross 0, or the opposite when we go from a 0 or from negative to a positive value. So this is how we can detect edges using the second derivative. Very important question would be, we don't have continuous functions, right? So this is how you calculate derivatives in continuous functions. But for us, we have a discrete function, and even worse, we have a 2D discrete function. For that, there is like an approximation for what are they called? For gradients, which is very similar function, right? So in here, we are trying to find the approximation of this, which is just basically, as we said, the change. So this is x. Let's call this x plus h. This is f of x plus h. And this is f of x. So basically, we're trying to understand this measure or this distance based on this measure, right? So the ratio between these. We're trying to understand how much a small change in x can lead to a change in the y direction, right? So in this case, we're trying to find it when h is very small. So h approaches 0. So we're trying to calculate this one when the h is really not that significant. But sadly, we do not have a value for like what is called this. So if you say the value of the image at index 5, I can give you the value. But if you give me index 5 plus 0, 0, 0, 1, there is no such thing for it, right? In this case, what we do is we approximate this limit, but instead of giving h a value that is very close to 0, we give it a value that is equal to an integer. So either 1, 2, 3, 4, something like this. But try to make it as small as possible, of course. There are three main forms to calculate these finite differences, which are very commonly used. So, yes, which are the following. So this is the forward finite differences calculation. Basically, it's f of x plus h minus f of x. There's the backward one, which is f of x minus h. And there is like the central one where we basically take, yes, this is x. Yep. We take one here and one before x, and we do the calculations between them, which basically all of them work, right? So the only thing that kind of interests us here is the fact that we are taking two consecutive steps, or we're taking, is the fact that we are taking the values of 2 pixels and removing them from each other. So basically, what this gradient calculation formula is, it's only a, what is it called? Help me out, guys. It is only a linear function of your image, right? So this is like 2 or 1. So this is a simple division. This is a pixel within the image. This is another pixel within the image. So it's just a summation of pixels inside the image. I think we don't really need to go through these stuff, but we could do like one calculation together, right? So here we're going to approximation by finite differences of h equals to 1. So in this case, I think they're going to use the forward method, right? So here we have 5 minus 5 divided by 1, which is 0, 5 minus 4. Oh, sorry, the forward method, yes. So 5 and f of x plus h is 5, right? So this 5 minus 5 divided by 1 gives you 0. And then we have minus 1. So this minus 1 comes from 4 4 minus 5. And then we have 3 minus 4, again gives you minus 1. 2 minus 3, again gives you minus 1. 1 minus 2, again gives you minus 1. 0 minus 1, again gives you minus 1. And then you have 0 minus 0, 0, 0, 0. 6 minus 0 gives you 6. 0 minus 6 gives you minus 6, and so on and so forth, right? So, now for the second derivative, once we have like the first derivative, we make the calculations again on these, on this one, right? We make the calculation again on the first, we make the derivation again on the first derivative, right? So if we derive the first derivative again, we will have the second derivative of the original function. Now, a very important method is don't do the derivation of the second function, right? So don't derive the first, so don't make the first derivative and then make the second derivative from it. You can calculate basically how it would look like. So this is what the first derivative looks like in the case when we have h equals to 2, right? Remember, so 0.5 times 2 gives you 1. And this one, okay, let me see. Minus 1, okay. Plus 1 and minus 1. Or in case if we would like to use the backward method, we would have this one. Now, if you derive or you take this as your function and basically derive it again, you're going to end up using the same formula of the discrete function. Here you will get the second form of your derivative, which is f of x plus 1 plus f of x minus 1 minus 2 of f of x, right? So this can be looked at as a, again, linear combination of the values of your pixels, right? Say this is the value at
but
x.
Should it be h instead of 1, no?
Can you repeat this?
Should it be h instead of 1?
H. Yes, but as we said, we replaced the h. We no longer work with h in general. We're working with a specific value of h, right? So in this case, we have either h equals 2 for the central, or we work with h equals to 1. Okay?
Okay.
Let's go back just a little bit. Maybe this was a bit too fast. Yes, so here we're going to be working in general with a small h, right? So we're trying to approximate h going to 0. So the limit of h going to 0. We can't get anything between 0 or anything at 0, right? Between 0 and 1. So the closest thing we can get to is 1. So 1 gives you the best approximation that you can have. Did you get that?
Yes.
So if you replace 1 in the formula again, so you're going to be dividing by 1 in here, which is simple. And again, plus 1 here. So it's kind of the same. So here you have this first function. If you derive it again, you're going to have this second function. So the second function, again, looks like a linear combination of your pixels, just so we can understand how this linear combination looks like. So this is the pixel at x. This is the pixel at x plus 1. And this is the pixel at x minus 1, right? Again, there are some pixels here and some other pixels here. Can you tell me what is the multiplier of f of x? Go ahead.
2.
Hmm?
2.
2. Look closely. Look closely.
Negative 2.
Nice. And the multiplier of f of x plus 1?
Positive 1.
1, 1. Very well. So in this case, basically calculating the second derivative ends up just by simply sliding a filter of 1, -2, 1, right? So this is how we calculate the second derivative. We don't really need to think of it as a very complex function. We can think of it as a small filter of 1, -2, 1. And this is what our friends thought of doing, right? We will get to that, I think, like right away. Yeah, we will get to that right now. So basically what the idea was, it's basically to calculate a derivative in the x direction and a derivative in the y direction. So in this case, if we would like to use the, what is it called? Central difference. So this was with the forward method. This is with the central method, right? So there are some differences. And here we are setting the value of h to be equal to 2. Why? Because the central method does not work with 1. So if it was able to work with 1, we would have used 1, but sadly it does not. So in this case, we would have this as the function or the formula for the derivative. And this is for the first derivative. Yes. So basically, again, it's kind of looking something like this, right? Let's look at it. So for, ignore this y, huh? Just complicates things here for now. So for the direction of x, we're not going to change the y, right? Now we're working in the image. Let's say we're at place x, y. When you're deriving in one direction, you're not going to be influencing, or you're not going to be thinking about the other one. So basically it's going to be f of x plus 1 minus f of x minus 1. So it's this one minus this one divided by 2. This is the formula for obtaining the first derivative. The second derivative, or like, yes, the first derivative in the other direction would be to fix x and move the y. But it stays again as the same formula. In this direction, we can see that -1, or the previous value, is still the same. The current is 0. The next is -1. So the -1, or the direction of the -1, kind of tends to depend on which formulation do you use. But overall, it will give the same results. So what we did was we combined kind of the two different filters that we had before, which is the first derivative in here. And remember this filter, which is the Gaussian smoothing filter, right? Wow. So now what we did is we simply combined the original 1D derivative filter with some blurring filter, just to give us some better results. And this is what gives you the Sobel derivative filter. This Sobel derivative filter, he didn't really just come up with this idea of using the blurring and smoothing filter immediately. Basically, he just tried different values, and this is the one that really gave the best results. And we will see that Sobel really wasn't the only person who had this idea. After Sobel did that, many people tried to play around with these values in order to get kind of the optimal values for calculating the edge detections, right? So in this case, we can have a Sobel filtered version for horizontal calculation, or for horizontal edges. And we have another one for vertical edges, right? So this one calculates a change in this direction. This one calculates the change in this direction. Very basic stuff, right? Kind of looks like an ordinary thing to expect, right? Yes, so what's going to happen in the image? How do we kind of calculate these derivatives? How do we get the gradients? And how do we use the gradients basically to do the calculations? It's pretty simple. You select your favorite derivative filter. We can say that we're going to use the Sobel filter for now, both for the, what is it called? horizontal and the vertical axes, we convolve them with the original image. And basically we have an output for this convolution as two separate images. The first image would be an image where we have the horizontal edges like focused on. Let's say it looks like this. The other image would be like an image where we have the vertical axes focused on like this. And then what we do is we combine these two and we compute the direction and amplitude of the gradients. The amplitude, very easy calculation, right? So this one, so it's the squared of the value of the pixel in here, plus the squared of the value of the pixel in here. And then we just put them through a, what is it called? Square root. So this is basic. Now the, what is it? Yes, this one. So the direction of a vector. So basically what we do is the following. Here, let's say we have a vector of values here. This is the vector that we are interested in. Nice. So from the coordinates of this point, we're going to calculate this angle between its this point, the reference, and basically the initial start or 0, 0. So this is how we end up with this calculation. Nice. I think we went through this already. Yeah, and again, if you would like to use the 3x3 Sobel filter, it looks like this. Of course, you can use other sizes if you want. And yeah, this is just so you understand, derivatives are very sensitive to basically changes, but they're also very sensitive to noise, right? So if you have an image like this, very good one. But if you just add a little bit, tiny amount of noise, you see how these images tend to, their gradients tend to get destroyed. Now, how do we use this in real life? Basically, we take an image, we calculate its x, well, we calculate its horizontal, what are they called? Edges, and then we calculate its vertical edges. So you can see in here, for example, these kinds of edges, they're shared between both horizontal and vertical, right? But if you look, let's find something where, yeah, for example, here, this edge is much clearer than the edge in here. And for example, this one, which is mostly horizontal, in here you cannot find it. I don't really make the distinction between horizontal and vertical, so yeah, I might have confused them, but you got the idea, right? So in this case, these are not visible here. And for example, the nose is not visible here. After that, what we do is we simply combine both of them using their, what are they called? Amplitudes, right? Or like the second norm of these vectors, right? So basically we get this combination, which is just the sum and then the square root of these intensities multiplied, and we get our pixel with edge detections. After that, you can just add like a simple thresholding algorithm, and you have your edge detection algorithm. Now, maybe we could go ahead and simplify this a bit further. So there is an application which is called the Laplacian filters, and I think we're going to, yes. Let's go quickly before the next lecture starts. Okay. So there is a simpler way to basically calculate the second derivative. So we said this for the first derivative. We could like make another pass through it and calculate the second derivative, but there is like a simpler calculation, which is this one, right? So this guy calculated for us the x derivative and the y derivative as the following. You change x plus 1, you change x minus 1, and then you do -2 f of x. So this is the similar to the formula that we found together before we studied this method. So we found this formula together. Now we're going to be using this formula and combining them both in the same filter, right? So imagine in this direction, we are doing 1 -2, 1. And in this direction, you're doing 1, another -2. Like this, 1. If you would like to combine them in the same filter, or like you would like to calculate basically something that does this exact task twice, so you would have something like this: 1, 1, -4, 1, 1. So this is how we combined both calculations of the second derivative in each direction. Now we end up with some values in these places with 0. So here we can set them to 0. And there you go. This is how you can apply the Laplacian filter, which kind of calculates the second derivative of your image, and it kind of directly focuses on the edges, right? So basically, the second derivative gives you this one, right? Or using the second derivative, you can get first derivative gives you where these sudden changes happened. No, sorry. Like this. And then this first derivative would look something like peak, and then it goes down. And then the second derivative would look something like this, right? So this is what we are looking at using the Laplacian filtered image here. And you can see it's actually not looking very bad. So it kind of highlights, again, our edges and our discontinuities. So this is just a small comparison between the two values this is for Sobel Y, this is for Sobel X. And this is how the Laplacian filter works. So basically he kind of combines both of them together, but for like the second derivative again. One question would be, why do we find these exact values for, like, why do we use them, right? So of course we know the mathematical basis, but can we use something like this? -5, 1, 1, 1, 1, and then we put like 0.25, 0.25, 0.25, 0.25, right? So why not do that? Why not combine this idea with the idea of like the Gaussian blurring filters that we have seen before, right? There's no right or wrong, right? If it works well, it works well. And this is what you can see in the Laplacian of Gaussian. So basically, instead of having just your filter being working only on these axes, right? So something like this. And all the other pixels here for your filter are set to 0. Why not try and do something a bit more creative like this one, and basically calculating the Laplacian filter, but mixed with like a little bit of Gaussian, what is it called? Noise removers or blurrers, right? So this is what the Mexican hat or the Laplacian of Gaussian filter does, and this is what it kind of looks like. This is the result of Laplace filter with smoothing, and this is without smoothing, right? So what we kind of actually did is just apply some blurring on the image in order to take away some of the noise inside the image. It kind of makes it more pure, more smooth for the edge detector, such that the edge detector doesn't detect a lot of edges, right? So it would detect the most minimum amount of edges possible. Now, Canny edge detector is like the best algorithm that we have for edge detection, and we will try to go through it. Let me see. Yeah, we'll try to go through it a little bit fast because it's quite simple. So if you understand the concepts of like gradient calculations, how do we do it? How can we represent gradients using just a simple filter, since the approximation of our gradients is just a linear function. And from there, things should be easy for you. So the Canny operator is a multi-stage algorithm designed to be an optimal edge detector. It's not being currently used for anything in industry, so do not expect to see it that much, but still it's a very interesting algorithm that you could take some ideas from. So first one is Gaussian convolution smoothing to remove the noise. As you have seen, applying some smoothing does help always. The second step is to find the intensity gradients of the image. An edge in an image may point in a variety of directions. So the Canny algorithm uses 4 filters to detect horizontal, vertical, and diagonal edges. So remember, we had edge detectors for like horizontal was we have values here, and zeros in this case. The one with we are working with. So we have values here, and zeros in this case. So he found also another calculation to do the diagonal edges. So basically we're calculating the edges here and we're calculating the edges here. Again, these filters were manually, or they took like a couple of years to manually find their values, but now we can find their values using convolutional neural networks directly, right? Edges thinning through non-maximum suppression. So basically, plus this noise removal, we're going to apply a non-maximum suppression algorithm. We will speak about non-maximum suppression algorithm, I think, in the object detection lectures, where we approach the end of the class, but it's a very simple algorithm. So basically, what it says is we only take the highest activations. You can think of it as some sort of thresholding, but more or less complicated than that. So basically, think of it as the adaptive thresholding algorithm, right? So it just goes through different regions and makes a threshold there. Thresholding and linking. So what they do is they define 2 thresholds, low and high, and they use the high threshold to start edge curves, and they use the low threshold to continue them. So this is just how they make the linking of the, what are they called? The different edges. So we take an example of how this algorithm works on this image, for example. It works very well, but you see here, for example, when we have small changes between this and this, when you do the blurring in the start, it kind of takes away these kinds of stuff. So you end up with something like this, right? So morphological processing, what we're going to use this is to kind of remove the majority of these impurities in the image, right? So if we could manage, so we have this, right? If we could manage to find an algorithm that kind of connects the dots here and connects the dots here, that would help us get to much better results overall. And this is what these morphological computations can give you, right? So just to go quickly through these things. So what we have is we are going to use some mathematical techniques to basically remove the imperfections, right? So we're trying to think of the world as a set of these kind of normalized shapes, right? And the 2 operations that we're going to use are the dilation and erosion, right? And there are like 2 derived operations which are called opening and closing, but they're pretty simple once you understand dilation and erosion. So let's go to what dilation is. So first we can speak about the structuring element kernel. So it has varying sizes and origins. Element values are 0s, 1, and none for other other possible values. Empty spots are don't cares. So this is what a box typically looks like. What we're going to do is we're going to convolve through an image and pass through it using this kernel and make some calculations. We will see, and this is how a disk kind of looks like, right? And we will see what are the calculations that we will be making. So for erosion, what we will do is erosion kind of shrinks the object. So apply the structuring element on every pixel. Remember the structuring element, right? So this is for disk, for example. This is the structuring element for disk. So what we're going to do is we're going to apply this structuring element on every pixel, IG for image F. IG is the center of the is at the center of the structuring element. And if the whole structuring element is included in the region, then we set the value to 1. Otherwise, we set the value to 0. So let's go back here and let's apply this structuring element using erosion. So it must have, if the whole structuring element is included in the region, then we call it 1. So if we come here, for example, at this place, so these are like zeros. Let's think of them as zeros, 0, 0, 1, and 0. So in this place, we don't have anything, so we put 0. In this place, also, we have just 3 parts of the structuring element included in the image, so we put 0. If we come to this place, for example, we have here 1, we have 1, 1, 1, 1, 1, 1, 1, and 1. So in this case, we have this structuring element fitting the whole area. So the output at this place would be 1. The output at this place, what do you guys think it is?
0.
0, right. So the structuring element does not fit the whole place. Of course, in this side, we do have 1, but in this side, we have zeros, and hence we take it out. So if you think of it correctly, or you think of it like logically, what it's doing is all of these pixels, it's setting them to 0. So it's kind of removing this external layer of the object. And this is what shrinking does. So this is what erosion does. Erosion kind of shrinks the object by removing some of its external elements. Dilation is like kind of the object opposite. So basically it expands the region. And if at least 1 pixel of the structuring element is inside the region, then we set its value to 0. So if we come back here, this point, what do we put in it?
1.
1, yes. Why? Because it has here 1 structuring element component, 1 structuring element component, and 1 structuring element component. So we said that we will set 1 if at least 1 pixel is shared between the structuring element and the image. And in this case, we have 3 of them. So we put 1 here. In this case, we also put 1, right? So we had 1 in here. We put 1, we put 1, we put 1, we put 1, 1, 1, 1 everywhere. And this makes our shape, or makes our object much bigger, right? So we're kind of expanding our object. So this is just a small erosion example. So we took away the majority of these places, and in this case also we took away some of these elements. So this is just a simple step-by-step explanation. So in this case, for example, we put 0. In this case, we put 0. This case, we put 0. This case, we put 0. This case, we put 1. This case, 0, 0, 0, 0. So if we look at it, we will have this in the output, right? This is an erosion example. You could go through this at home later on and do it slower. For erosion, for example, we could use this technique to calculate the number of coins if they are closer together. So basically, our method would kind of create holes between the different coins. Basically, how is it creating these coins? It's by eating the components or eating the objects in the image one by one, and basically creating much more bigger distance between them, allowing for easier calculations. As you can see, this is like, depends kind of on the size of this filter. So if we use a small filter, we would have something simple. If we use something very big, then we would eat a lot of pixels and a lot of impurities. This is what dilation looks like. So this is the dilation is kind of the opposite. Remember, previously this shape got even smaller, but with dilation it gets even bigger. So what is it used for? For example, to repair breaks or repair intrusions, right? Or to fill these values, remember. So this is just a small example of what dilation looks like. This is how dilation can be used. For example, restoring historical images, making them a bit clearer to read. And basically what we will be doing is that we could combine erosion and dilation into two a bit different, what are they called, calculations. First one is opening. So opening, what it does is simply creates an opening as it says in the original shape. So the opening of image F by structuring element S, denoted F of S, is simply an erosion followed by a dilation. How can we remember which one makes smaller and which one shrinks and which one makes it bigger? So for me, I like the D kind of represents like some, I don't know. For me, D kind of looks like a big alphabet. And here I just remember the O, kind of a small alphabet. So erosion makes it smaller, dilation makes it bigger. Just like a small trick for you guys to remember which one is which, because some of them could be a bit misleading. So erosion, what it does is kind of removes this connection, and then dilation does not build the connection again, but kind of builds back the original shape, right? So what happened is we removed this one using erosion, but because of erosion, we also removed some of the pixels here, right? And we fix that by adding dilation, right? So if you apply erosion followed by dilation, you would get this opening and you would get kind of restore the original shapes. And this gives you only the opening, right? So erosion does opening plus destroying the object. So we fix this destroying part by adding the dilation. And kind of they take away each other and you get only opening. So this is how opening is done. This is just an example of opening. Now closing, on the other hand, is done by the opposite direction, right? So we use dilation first to make the object a bit bigger. So for example, we have this kind of hole in here. If we use dilation with a very big filter, we would get this part completely covered. If we use, what is it called? Erosion after it, then we would kind of reconstruct the original shape. So again, what dilation does is that it closes plus kind of, how do we say the opposite of shrinking? Makes it big. Makes the object much bigger.
Extend
So
object.
Can you repeat?
Extend object.
Yeah, we extend the object, right? So if we use erosion after this dilation, we kind of remove this big or dilation by shrinking the object. So they kind of take away each other and you get only the closing part done. So this is just a small example of what closing looks like. So you see, this was completely removed. Yeah, morphological, the morphology of boundary extraction. This is actually a quite useful technique. So this is just another way to do what is that thing called edge detection. Simply what we do is the boundary of a set A, denoted as boundary of A, can be obtained by first eroding A by B, and then performing the set difference between A and its erosion, right? So what we do is we erode the object, make it a little bit smaller, and then we take the big or original one and remove the small one, right? So this one gives you this edge detection algorithm. You could do the opposite by like using, for example, dilation, and then you take the dilation minus A, so the big one minus the small one, and you would have something very similar, but just like the edge would be on the outside. And I think that's it for this lecture. Did you guys cover this lecture in the lab already? Did you guys cover dilation, erosion, edge detection in the lab already, or not yet?
Not yet.
Not yet, very well. So I think we could start the next lecture. Do you need like a 5-minute break or something? This lecture is pretty simple, honestly. It's about object detection, but all of it is like very basic calculations, very, very basic stuff. That's, yeah, very, very basic stuff. Template matching, basic stuff. Histogram gradient is kind of an important algorithm, but we will go through it very basically. And then SVM, you already know this. Active contours, also they're very basic. We will not go to them in detail. I think let's take a 5 minutes break and we go through this lecture again, okay? Oh, yeah, I'm not muted. Hello, everyone. I hope you guys are back. And today we're going to speak a little bit about like old techniques for object detection, right? None of these techniques is being used now, but still. This lecture is pretty easy, but also pretty useful at the same time. So we will speak about like connected components. Then we will speak about connected components labeling. And maybe you guys would see the similarities between this and some of the clustering algorithms that you have studied before. Then we will speak about object detection and how it's done using template matching, image pyramids, and histogram of oriented gradients. And then the active contours model, we're not going to go into detail about them. We're just going to present 3 different algorithms and tell you which one is best, and you guys could just use that function through Python. So what is connectivity? So connectivity is defined by relationships between pixels. So let's say this is like how 4 neighbors would look like, and this is what 8 neighbors would look like, right? So a connected component is a set of pixels in which each pixel is connected to all the other pixels, right? So let's say that we define this connectivity based on some sort of distance measure. If, let's say, this pixel minus this pixel is smaller than 10, they are connected, right? So this is what connectivity kind of looks like. So this is, again, a small definition. This is pixel XY. This is its neighborhood or 4 neighbors, and these are its 4 diagonal neighbors. All of them represent its 8 neighbors, right? So let's do a small calculation here. So how many objects do you find here, and how many connected components do you see in here? Let me do the following. Sorry. Nice. Sorry. Let's use not this one. I think I want to use this one. Okay, let's use this one. So this pixel, for example, let's put it here. Do we have a connected component in this area? Where all of the 8 objects are connected with each other. Sorry. Did you get it? Let's do it. So here we will start from, for example, this place. We will try to find if there is any connectivity inside this object, right? So here there is nothing. It's not connected to anything, so we can skip this. We can easily just go, for example, to this one directly, because we can skip all the places which don't have any values. So we start here. We apply our 4x4, 2 by or 3 by 3. Yeah, this is 3 by 3, and we check this 8 connectivity. We can see that this pixel is connected to this one. This pixel is connected to this one. So we have this one. We continue. We move to this one. We see this is connected to this, and this is connected to this one. We move forward. We come here. We see that this one was already connected, so it's done. This one, let's connect it with this one because it's its neighbor. Again, we move. We come here. It's connected. It's connected, right? So overall, we have what is it called? We have 1 connected component, right? They're all linked together. But if we don't use these, what are they called? Diagonal connections, or the 4, this, yeah. If we use just the 4 connected object without these 4 diagonal points, now if you put this one on our image here, we will not have anything, right? So nothing here, nothing here, nothing here, nothing here. So it's done. Here we will have these two linked together and these two linked together. And this one is also nothing here, nothing here, nothing here, nothing here. So it's a connected component on its own. Sorry, shit. Nice. So here what we have is using the 8 connected object, we can find only one big component. By using the 4 connected objects, we could find only, but basically different 4 objects. If we had this also as a pixel activated, this one is an activated pixel, this one is an activated pixel, and this one is an activated pixel, or just these 3, for example. If we had it like that, then all of them would be connected with each other like this, using even the 4 connected object. Nice. Connected component labeling is like an algorithm that's similar to clustering, right? So if you guys remember dbScan, or you already, you told me you guys don't remember it that well because you took it in the last lecture, but it's very similar to these things. So what it does, so let's skip this. So let's look at it. So it's important to note that we only apply connected component analysis to binary or thresholded images. So given an RGB or grayscale image, threshold it based on some criterion in a manner that can segment the background from the foreground. So this step, we already did these things in the last lectures, right? So you remember how do you find this adaptive thresholding techniques. And once we have obtained the binary version of the image, we can proceed to analyze the objects. So the first pass, in this first pass, very basic pass, each individual pixel is given its own label, or if it's connected to a previous label, it's given that previous label, right? So for example, if I'm working here, sorry, let's do it like this. So I found a 1 in this pixel, or an activated pixel, and I didn't find anything connected to it from something that I've done before, so I give it label 2. I went ahead, there was nothing here, there was nothing here. I found an activated pixel here, so I give it label 3. I go down, I find an activated label here. It is connected to a previously labeled component, so I just give it 2. And then you continue your work until you finish the whole image. Once you did that, kind of go through the whole image again, but instead of just merging, instead of just seeing if it's already connected, now you're going to connect all of the connected components that might be connected. So let's look at it into an image. So this is the image. This is how it looks like in a representation of a function. And this is how it looks like in a matrix. So it looks kind of ugly in this case. So now we're going to invert basically the zeros into ones and the ones into zeros, just for ease of interpretability or understanding by the students. So in this case, you can see that we have 1, 1, 1, 1, 1, 1. Again, if we use the 4 connected components, we will have 1, 1, and this is another component. So these are like 3 components. But if we're going to use the 8 connected components, all of them are going to merge together. So let's do it. Okay, so we're using the 4 connectivity components. Okay. Wait a second. There is a 1 in here, right? Sorry, there is a 1 here. So it would look like this even with the 4 connected components, right? Yeah. So let's start applying it. 0, 0, 0, 0, 0, 0, right? All of these were intentionally 0, so we don't work on them at all. This one was a 1. And as we said, this is the first one that we have. So it's not connected to anything before. We put it as 2. This is 0, again, very simple. Now this 1, is it connected to a previously existent label?
No.
No, so we give it a new label, right? So this one will be 3. 0 again, 0, 0. This one, is it connected to a previously existent label?
Yes.
Nice. So we give it 2. This one is also connected to a previously existent label. We give it 2. This one, as you guys wish, right? So you could put it as 2, or you could put it as 3. Both of them will work at this stage. Why? Because these two components, which kind of share this pixel, will be connected together later on in the second pass, right? So here it's 2, and there you go. This is what you get. With the second pass, what will happen is you will go through all of these pixels. If there are components, so this is label 3, and this is label 2. If these two components are kind of close together, they could be like connected using this connectivity for connectivity, then we just merge them into the same label. In this case, we merge them into 2. We could merge them into label number 3, really does not matter. So this is just another example of how it would look like with the first pass, how it would look like with the second pass. So you see this one was not merged with the others. So object detection, first, what is object detection and how is it different from image classification? What can be an object and why is object detection hard? So these are the questions that we will be asking now. So object detection is a very simple technique. It's quite similar to image classification, but now in plus of it or something extra, we're not just going to detect whether this is a stop, there is a stop sign in the image, but we're going to answer another question, which is where is this stop sign inside the image? So this is what object detection does. So here you can see we have railroad, stop sign, and we have their location. So image classification is what is inside the image, but I don't care where is it. So we have a boat and we have a person. The object detection answers both questions, what and where. So these are just some basic examples of objects inside images. So this is the basketball hoop. Yeah, objects in the real world can exhibit substantial variations, especially, for example, if you look at this one, you look at this hoop, they're very different from each other. These variations can be a variation in viewpoint, scale, deformation, occlusion, illumination, background clutter, and inner class variation. I think inner class variation is the biggest problem we have. The rest, we can all fix them with more images and better cameras, but intra-class variation is the hardest problem. So these are just like some of the application: facial detection, motion recognition, just detection of stray spots inside parkings. This will be like our last homework, not homework, our last lab. The detection of stray spots in parking. Sorry. Approaches to object detection. So there is the basic approach, which is like more structured approach that kind of thinks of the world as just a combination of different structured shapes, right? So this is what appearance-based template matching is trying to do. So basically it thinks of a car. All cars are kind of the same thing. They're all the same shape, right? But it could be like rotated or something like that. But in reality, they're all this rectangular box. Now, template matching, what it does is it tries to basically find the location where two images are similar. So we have this template image, let's say this cup, and we're trying to find the location of a cup inside our image. So what we do is we will slide our cup through the image and do a pixel by pixel comparison. If the pixels like if the difference is smaller than a certain threshold, we say there is a object here. If there is not, if it's bigger than a threshold, we say there is no object in this area. Again, the similarity or the differences are calculated in two different ways. First one is, first one is mean squared error, MSE. The second one is cross correlation, right? Yeah, there are two different techniques. So this one is commonly used for regression problems to evaluate them. This one is used to like calculate the loss for classification tasks. Both of them are correct measures of similarities. So it's just a hyperparameter for your method. One big problem of this method is the size or the scale, right? So for example, if I'm working on this image and I have my cup like this size, right? So this is the size of my cup in the image. If I fit it through the image here, it's not going to find anything. Let's say my cup is this size. I have a very small cup. So if I make this pixel by pixel comparison, it's not going to work. So they proposed like a simple method. This method was like proposed and then later on, well, how do we say it? Ignored, but now it made a very strong comeback, this image pyramids technique. So previously, again, it was done as a simple algorithm where we compare that template image on this one, and then we compare the template image on this one, and then we compare the template image on this scale, and then on this scale, and then on the last scale. So this one kind of simplifies or kind of like overcomes the problem of scale in our original image, but still it doesn't work really well. So they proposed a different or a better algorithm. Let's talk about it here before like going forward. So here we understand the subsampling part, but can somebody tell me why should we blur the image before we subsample it? Why would it be useful for us to blur an image before we subsample from it and get the next ones? What does blurring do for you? Mm-hmm.
Maybe we, okay.
Yeah, go ahead, yeah. Go ahead. Somebody's shy. What does blurring do, right? So remember, blurring applies this kind of kernels or something different. Basically, what it will do is it will, at every pixel, will have kind of a combination of its neighborhood. So later on, when you subsample, if you take this pixel or 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 this pixel, you will always have some of the information of the other pixels. But if you subsample directly, you're kind of losing, for example, all of this region, you only take one pixel. Certainly that one pixel will not be representative of the image as a whole, and your subsampling would look like this. So for example, this is the 1/2 subsampling, 1/4 subsampling, and 1/8 subsampling. So in this case, you can see that it's getting very ugly. It's getting very difficult to work with. Why? Because when we subsample, the pixel that we might have chosen might not be very representative of its area. But when we apply Gaussian noise or Gaussian blurring, we get this kind of effect where every pixel is a combination of its previous neighborhood, and the image kind of stays overall much better, right? So this is why we do this blurring, downsampling, blurring, downsampling, blurring, downsampling, blurring, downsampling. Yeah, so basically match template at current scale. This is the algorithm, match template at current scale, downsample the image. Downsample means blur and downsample, of course. Repeat 1 and 2 until the image is very small, and take the response above some threshold, perhaps with non-maximum suppression. Again, non-maximum suppression is an algorithm that is still very commonly used in all object detection models that kind of removes overlapping predictions. Yeah, I think we're going to have to definitely explain non-maximum suppression a bit earlier than object detection, but it's a very simple one, right? So as we've seen, this object detection technique still suffers a little bit from scale and location problems. So what they proposed is another algorithm called HOG combined with a classifier such as SVM that kind of overcomes the problems of scale and object detection right? So HOG is called histogram of oriented gradients. It was created in 2005, so it's pretty easy, it's pretty recent, and it was made in CVPR conference. So CVPR is a very well-known conference, and it's called histogram of oriented gradients for human detection. So HOG uses a global feature to describe a person rather than a collection of local features, right? Remember, this template image, this is how we are describing our object, right? So we're kind of describing an object as a collection of local features. And now the entire person, we're speaking about a person instead of an object just because the original paper spoke about human detection, is represented by a single vector, not by many feature vectors representing smaller parts of a person. So an SVM, or support vector machine algorithm, usually is trained to classify these HOG descriptors of people, positive samples and negative samples. So HOG is a feature descriptor that is often used to extract feature from image data. And actually, it's still till now being used. For example, in cases when you don't have a lot of images, you can still find people using HOG as a feature descriptor. And it is widely used in computer vision tasks such as object detection, right? So the first step is to pre-process the data. Second step is to calculate these gradient histograms and then normalize these gradients and then combine them into this feature descriptor. So the first question is, how do we calculate gradient histograms? Very simple, very basic technique. We take all images of the same shape. Why exactly this shape? Well, this is the shape that they used in the original paper. You can use anything else that you want, right? So what we do, we split the image into these 8 by 8 pixels. And then within each cell, we compute the gradient vector. How do we compute the gradient? By using either Sobol or any of these other kernels, right? So at this 8 by 8, I apply Sobol and calculate the gradients. Sorry. Once I have the gradients, I will put their values in here. Remember, from the gradients, we can extract two different values. The first one is the direction of the gradient, and the second one is the amplitude of the gradient. So what we do is we put, for example, I found an extra gradient with direction 150. So I put extra point here. How much extra point do I put? I put exactly the amplitude of my gradient. So this is how I create this histogram. I start from an empty histogram. Every gradient, I calculate its threshold, its angle. For example, its angle is 70. I put the 70 here. The size of this one would be the amplitude of the gradient. And then I continue so on and so forth until I have this kind of histogram in the end, right? So how do I calculate the gradients? Again, you can use either Sobol or any other gradient calculating algorithm. And from the gradients, you will be calculating either calculating two things, which is the direction and the magnitude or the amplitude of the what are they called? The gradients. And then from there, you will split them like this. So here we have the same pixel, this blue pixel, 80 degrees to amplitude, right? So what we do is we come to this 80 bin and we put 2. This one, for example, this is 4 with 25. 25 is definitely between 30 and 10. So what we do is we split its amplitude between 30 and 10. If you have 50, you put it directly in the 50. If you have something between 50 and 70, you kind of split it between 50 and 70. This is just how they decided to do it. You could have just taken the bins directly by using, what are they called? These intervals, but this works. So after that, after we have this binning and we have these histograms, we will be kind of normalizing the histogram. So this is the histogram for one 8x8 region. We have another histogram of the 8x8 region that is next to it. So what we do is we combine these two histograms and normalize them together, right? So what we do is we normalize the histograms so they are not affected by lighting variations. Rather than normalizing each histogram individually, the cells are first grouped into blocks of 2x2 cells and then normalized based on all histograms in the block. The blocks have 50% overlap. So for example, here we have 8x8, 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 and then we normalize all of them based on, what do we call it? Yeah, we normalize all these 4 different histograms based on each other's weights. How do we do that? Or how do we normalize a vector? So this is, for example, the first 8 values represent the first histogram, the second 8 values represent the second histogram, the third represent the third histogram, and the fourth represent the fourth. This is how we calculate the norm of a vector, or this is how we calculate the norm of a vector. Simply, it's the square root of the sum of its individual components squared, right? So this is how we calculate it. After that, we normalize it by simply dividing all of these by k. And this one gives you a h for which its norm is equal to 1, right? So normalization is something that you have definitely done a lot before. So this is what we do for it. After we have these 4 histograms of 9 bin, 4 histogram of 9 bin per histograms, here they are. We normalize their gradients, all of them together, and then basically combine them in order to get this feature for complete image. So what do we have in the end? We have 105 blocks multiplied, which are 15 by 7. Each one of these 105 blocks have a vector of 36 by 1. What is 36 by 1? So it's 4 by 9. Basically 4 cells. Each cell has 9 bins. Hence, the total features for the single image is, well, this multiplication, and you end up having 3,780 features for the whole image, right? Definitely, it's a lot lesser than the original size, but it's much more, but it's still kind of big. So training a model on this one will require some amount of data, and definitely training a simpler model such as SVM would give you better results. So for now, we can stop here. Next time, we will speak about these different contour algorithms, but most importantly, we will have a quiz first about these things. And definitely, we're gonna have a very, very detailed recap about all the things that we have seen today. I don't think we have enough time for questions, so no worries if you have some questions for now. We can save them on for the next session where we will have like in the start, we will have a place for questions, and then we will have a time for a very detailed recap of everything we have seen today. And then we will have our quiz, and we continue on for active contours. So thanks a lot for attending. And I will upload the lecture for the previous course right now.
Thank you. Goodbye.